Okay, welcome. Day 2 of chapter 3. And again, we're still talking about bivariate data and our least squares regression line. We're going to talk a little bit about slope, the y-intercept, predictions using our least squares regression line, and extrapolation. Okay, and we want a sort of guiding concept again of what is going on. And this time what our guiding question is going to be is, can we correlate attendance and scores? And we're going to use the Algebra 1 star test. So we're looking at what we've traditionally seen is that if there is a high poverty rate, there is low attendance and low scores. But if we could change that attendance to be high attendance, would that cause our star scores to increase? So these are the data we're going to be looking at today. And within this data, we will be learning about some of these topics. And so our first one is going to be our percent attendance and the average or the star score that students got. So our explanatory variable, we think it's going to be the percent of the attendance. And we think that's going to explain the response, which is going to be the star, Algebra 1 test score. So we think the attendance will explain what's going on, with our star score. And here's what the data looks like if we were to plot it. Well, if we were just looking at that, we might say that that does look like the percent of school days attended versus the star Algebra 1's raw score appears to be linear, positive, and I would say moderately strong. But how do we find the actual line that goes through here? So that's what we're going to be talking about. So let's flip this over and take a look. And when we flip it over, here I've got just 3 different data points, and we want to talk about how we use this. So instead of using the distance from the point to the line, the point here or the point from here to here, if I just use the difference from these, well, this is a positive difference and this is a negative difference. When I add those together, they cancel each other out. So I would say that there is no error. Well, that's not true. We can see that that line does not go through all 3 points. So instead, what we're going to have to do is what's called squaring the difference. So the difference here then form a square, so same distance. So squaring that gives me this distance. Squaring this difference gives me this. So notice when you square it, you always get a positive value. When we add those together, those are our variances. When we add them together and take the square root, that tells us how far the line is off. And here's one much better line, obviously, that it goes through all 3 points, so there is 0 error. So if the sum of the squares is 0, that tells us that the line is perfect. Here, the sum of the squares is 8, so that's not the best fitting line for those same 3 points. So again, the least squares regression line is a linear model that's going to minimize the sum of the squares of the residuals. And let me define the residuals for you in just a second. Residuals is the difference from each point to the line. That's called your residual, how far away you are. And the way we calculate our residual, I can't remember where I'm supposed to put this, but the residual for each data point is your actual data point minus the predicted amount. So the actual data point minus the prediction here. The actual value minus the prediction. So actual minus predicted, that gives me a positive value. In this case, the actual minus the predicted is a negative value because it's below the predicted value. And the way I like to think of this is residual is AP, advanced placement. So actual minus predicted. Some people say observed value minus predicted. I just like to think of it as AP because that's easier to remember. Another, you may have heard this called the line of best fit. In algebra, that's more likely what we would have used. So here is my data for my attendance. So my percentage of school days attended versus the star score. And you can see that we've built these little squares. So it's my residual squared in each case. And we're going to add all those together. Okay? So the line of the least squares regression line model is going to be the one that minimizes the sum of these squares. And again, there will be a formula for this. We do not want to do it by hand by any stretch of the imagination. Okay? So we could do it, we don't want to. So that is how we find the line. It's going to have the smallest sum of the squares. We want to talk about the slope and the y-intercept now. So in Algebra 1, we would look at the line of best fit in this format, y equals mx plus b. M would be your slope, b would be the y-intercept. In statistics, our least squares regression line is going to look like this. Y hat, so that little funny thing on top of it, so it's going to be a y with a hat, like a caret on it. We just call that y hat, is going to be equal. We put the y-intercept first, and then here's our slope. So again, here the m represents slope, here the b represents slope. So it's going to get a little bit tricky on a calculator, making sure we remember what they represent. And here, this is your y-intercept. And on the stats linear regression, the y-intercept comes first. And it's just how it's done in stats. It wouldn't be wrong, like if I wanted to rewrite this equation, say 0.57x minus 7.69, I could. It's just not the way we do it in stats. I know, it's kind of annoying, but that's how it is. And coming back to this y hat, that has a special meaning. The hat on there means predicted. And that's going to be very predicted. Very important that we make sure we say predicted value. So this is my predicted value here, the least squares regression line. So y hat, and anytime we write this out and you're asked a question about what the least squares regression line is, we would say the predicted test score is given by negative 7.69 plus 0.57 times the percentage of attendance. So you have to make sure you're identifying the variables. You can put predicted test score right here, and you can put the percent attendance here, or you can write them below like it's done here. But that word predicted has got to be in our answers. Okay, let's go on to the next page and take a look. So here again was my least squares regression line. So it is the predicted test score based on this equation of negative 7.69 plus 0.57 times the percent attendance. If I'm going to interpret this, which of course you're going to be asked to do, the sentence stem, and you might want to highlight this for yourself, but this stem you would use anytime you see this question, interpret the slope value. You're going to answer for every 1 unit increase in the explanatory variable, and of course you'd put what your explanatory variable is. Our model predicts, and I guess you've got to have that word, predicts, an average, an either increase or decrease. So if your slope is positive, it's an increase. If it's negative, it's a decrease of, again, what the slope is in the response variable. So in this case, I would say for every 1 percentage point increase in attendance, excuse me, percentage, our linear model predicts an average, and it's going to be here, my slope is positive, so an average increase of 0.57 points in the student's star score. So again, the unit, in this case we were talking about percentage, the explanatory variable was my attendance percentage. And I'm putting linear so that they know I know what I'm talking about here. It's a linear model, and it predicts. If that word predicts is not in there, you're not going to get points. and an average increase of whatever your slope is. The slope is 0.57. So as x increases by 1 unit, my response variable will increase by 0.57 units. Okay? To interpret the y-intercept, that simply means that what if your explanatory variable was 0? Right? That's what the y-intercept is, the x value, or the y value when x is 0. Well, if x is 0, x represents the increase in attendance. Or sorry, not the increase. That's your attendance percentage. So when the attendance is 0%, our model predicts that the uh, student's star score would be negative 7.69. Because again, here's my sentence stem, just like we had for the slope. That makes no sense. So if I were to write this, when the attendance is 0%, our linear model predicts that the student's test score would be negative 7.69. Makes no sense. Is the y-intercept meaningful in this context? Explain. No, it doesn't make sense because here, I'll just show you it is not meaningful since anyone with a 0% attendance doesn't go to school or doesn't take the exam. I mean, if you're not in school, you can't take the exam. Also, we can't have a negative value on the STAR test. So the y-intercept is meaningless in this case. If we want to make predictions using our least squares regression line, which is the whole purpose of creating one, the district says, what if our student meets the minimum attendance of 87%? What would we predict their test score to be? Well, that simply means that I'm going to plug in 87 right here and see what the predicted y value is. Remember, the y value is the response variable, the math score. So what I would do is I plug it in, keeping that little hat on my y. So I have 0.79 plus 0.57x. I'm putting the 87 in for the x. So I would predict a math test score of 41.9 points with an attendance of 87%. That's all it's doing, and it's predicting what score we would get. Okay, let's take a look at the next page. This is just more of the discussion. Again, remember our overarching question was, if we increased attendance, would that increase test scores? And so this one particular school district did that. They called students who were chronically absent. They hired attendance case managers. They worked and got Uber and Lyft to bring students to school who had transportation issues, all sorts of different things. And what they found was, yeah, attendance increased. That was great. But the test scores didn't. So again, there's got to be some underlying issue here. Remember last time when we were talking about the amount of ice cream sold and the amount of drownings? While they did the same thing, it didn't make sense. There was no causation there. In this case, the attendance isn't solely the cause of the test score. So just increasing attendance did not increase our test scores. So overall, our test scores did not rise significantly, and the achievement gaps remained. But so something to think about, what could we do to help increase test scores? And this is the battle for all educators. How do we help people increase test scores? As a society, we have poverty, but how are we going to deal with that to help increase test scores? Again, we're talking about the dangers of prediction. So the very last thing we're going to take a quick look at here is this doctor at UNC published a study on obesity. And this said that over time, from 75 to 2010, they looked at the percentage of US population that was overweight. And look at this is an extremely strong positive trend here. But can we use this to predict that, say, what about in the year 2048? 100% of Americans would be overweight. Does that make sense? Because based on this, it does look like that's what's going to happen. Well, over here, I've extended out to go to 2048. So about right there is 2048. But look at how far that year is from this interval where we gathered the data. It's not within the interval. So when you are trying to make a prediction where your data value, your X value is way outside the interval where you gathered the data, it's not going to be accurate. Or it might not be accurate. You can't say 100%. This is what's called extrapolation, where you're extrapolating what's going on here to something that's going on way over here. Extrapolating is not a good idea because you can get very incorrect data. So we do not want to be extrapolating. Okay, so again, this data was gathered from 75 to 2008, I believe it was. Sorry, 2004. So if we used any of the years in there, we could certainly predict what the obesity rate would be. But when we get outside of there, it's not so accurate. Maybe even 2006 might still be accurate, but as we get further and further away from this data, it's not going to be an accurate prediction. Okay, and that's what I have for you on this unit, and I think you've got it. So go ahead and take a look at the homework now.